Artificial intelligence is often described as the science of creating machines capable of human-like cognitive functions. It sounds like something out of science fiction, involving machines that can learn, reason, and solve problems independently. However, for the engineers and technical leads building these systems today, the reality is much more grounded. We are not building conscious entities. We are constructing complex data processing pipelines that excel at specific tasks. The definition has shifted from a singular concept of intelligence to a spectrum of capabilities. Most of what we deploy today falls under the category of narrow AI. These are specialized tools designed to handle pattern recognition and decision-making within a constrained environment. Here is the thing that often gets overlooked in the excitement. The transition from theoretical research to production deployment involves a massive shift in priorities. In an academic setting, the goal is often to push the boundaries of what is possible. In a production environment, the goal is reliability, cost efficiency, and maintainability. You might be working on a model that achieves state-of-the-art accuracy on a benchmark dataset, but if it requires a graphics processing unit that costs thousands of dollars per inference, it will not survive in the real world. This creates a fundamental tension between performance and practicality. Consider the architecture of a modern machine learning system. It is not just a single script running on a server. It is an ecosystem. You have data ingestion pipelines that must handle vast amounts of information from various sources. This data must be cleaned, normalized, and prepared before it ever touches a model. This is where the old adage of garbage in, garbage out holds true. If your input data is noisy or biased, no amount of algorithmic sophistication can compensate. The engineering effort often focuses more on the data quality and the infrastructure surrounding the model than the model itself. Once the data is ready, you move to the training phase. This is where you consume significant computational resources. But the work does not end when the training stops. You must then deploy the model into a serving environment where it can accept requests from applications. This is where the trade-offs become critical. If you are building a real-time chat interface, latency is your enemy. You need responses in milliseconds. If you are building a batch processing tool for financial analysis, accuracy is your priority, and you can afford to wait minutes for a result. Deciding which path to take requires a deep understanding of your user's needs and the constraints of your infrastructure. Scaling adds another layer of complexity. A model that works for one user might break under the load of 1,000 concurrent requests. You need to think about load balancing, caching strategies, and horizontal scaling. Do you replicate the model across multiple servers? Do you use a specialized inference engine to optimize the computation? These are not theoretical questions. They are daily decisions that impact your budget and your user experience. Many organizations underestimate the cost of inference. The initial training cost is often a one-time expense, but the cost of serving that model grows linearly with every user interaction. There is also the issue of model drift. A model trained on data from last year might not perform well on data from today. The world changes, and the patterns the model learned might become obsolete. This is why monitoring is not optional. You need systems in place to track performance metrics over time. If the accuracy drops, you need to know immediately. This might trigger a retraining cycle, which brings us back to the infrastructure challenges. You need a pipeline that allows you to roll back to a previous version if the new one fails. This version control for models is just as critical as version control for your application code. Now consider the broader implications. There is a debate about whether we are in an economic bubble or a genuine revolution. Some experts argue that AI will revolutionize sectors without diminishing human capability. Others warn of regulatory gaps and risks to job security. The truth likely lies in the middle. AI is becoming a collaborative partner that augments human decision-making rather than simply replacing labor. This shift requires a new mindset. We are moving from a world where machines execute instructions to a world where machines suggest actions. This brings us to the ethical boundaries. When a model makes a mistake, who is responsible? If a diagnostic tool suggests a treatment that harms a patient, the liability is complex. This is why transparency and explainability are becoming key requirements in the architecture. You cannot just have a black box that gives an answer. You need to understand why the model made that decision. This adds overhead to your system but is essential for trust and compliance. Furthermore, there is a distinction between traditional artificial intelligence and the newer generative capabilities. Traditional systems rely on programmed rules for precise analysis, while generative systems create novel content. This distinction matters for your architecture. A rule-based system is deterministic and easier to audit. A generative system is probabilistic and can hallucinate. You must design your systems to handle the output of these models with verification layers. This ensures that the creative output does not introduce errors into your business logic. The democratization of this technology is accelerating through open-source repositories and beginner-friendly curricula. This is transforming artificial intelligence from an academic niche into a foundational skill for a broader range of developers. However, this accessibility brings responsibility. When anyone can deploy a model, the risk of misuse increases. Your architecture must include guardrails to prevent abuse. This might involve rate limiting, input validation, and content filtering. These are not just technical features, they are ethical requirements for a sustainable deployment. Ultimately, the technology's utility in automating repetitive tasks is undisputed. But the long-term impact requires careful navigation. The consensus on how to balance rapid innovation with necessary oversight remains incomplete. As a technical leader, your role is to build systems that are robust enough to handle the uncertainty. You are building the foundation for a future where artificial intelligence acts as a reliable tool rather than a mysterious force. The goal is not to replace human judgment, but to empower it with data-driven insights that were previously impossible to access at scale. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.